Hey guys, and welcome to a new video in this computer vision tutorial. In this video we're going to do a project over what we've been going over throughout this tutorial. So we're going to combine some of the things that we've already learned, and we're going to do some detection of circles, and also we're going to do some calculations with some camera geometry of things we've learned in this tutorial here. So this is a project to like summarize some of the things we've learned and try to do some to do a like more practical project and use some of the things that we've learned in the tutorial. But first of all, make sure to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you also want more in the future. I really appreciate your support, and it just helps me and the YouTube channel out in a massive way. So let's jump into the project here. And the first slide here is the project overview, like what we're going to do in this project here. So in this project here, we're going to detect some models in an environment, and we're going to use the half circle transform built-in function from OpenCV that we talked about in one of the previous videos. And then we're going to localize the marbles that we've detected by calculating the angle to the marble and also the distance to the marble by using a monocular camera geometry. So these will be estimates of the angles and the distances to the marbles, because we only have one camera and we don't have any information about the depth in the image by only using monocular camera. Then we're going to test it in a simulated environment. I'm going to show you how that program works in a bit. So I'm going to show you the result first, and then after that we'll dive into the code, see how we can code this application and how we can do these different kind of calculations. And then last of all, we're going to like have this tuning of the parameters. So we're going to test it in the simulated environment. Then we can tune some of the parameters, see like how we can talk between our C++ application and the simulated environment that we're going to use. So in this project here, we're going to use the Gazebo simulator to simulate what we create with our application in OpenCV and in C++. So we're not in the Linux environment here, and I'm going to show you the Gazebo simulator that we're going to use for this project here, where we can have a robot driving around in the environment, and then we can tell it what to do, and also like get the information from the robot's lidar and also the camera, and then we can create our own application in C++, and then we can apply that in the simulator and see like how our code works in the simulator. So first of all, here we're going to create a Gazebo server where we're going to run this small world program, or like this environment here. So if we hit enter here, we'll create this server where our small world environment will running, and we can see that we have successfully opened or like created the server here, and we're connected to it. And then we can create a client here where we can actually like run the Gazebo simulator. So this will open up the Gazebo simulator here, and we have this robot here, which is equipped with a camera and also a lidar scanner. So all these blue points here is the lidar scanner's measurements, and the wide range here is the camera's field of view. So we can see that we have this robot here that can drive around in this environment, and we have these two rooms here with the marble here that we're going to detect, and also we're going to calculate the angle and also the distance towards that marble by only using a single camera and by using camera geometry. So if you go into the program here, first of all, I just want to show you like how it works, and then after that, when we have seen like how it works and also like what we're going to do in this project, I'm going to show you like how the code works, and also like what different kind of changes we can make, and also like just like how the code works and how we can have it running in this simulated environment here. So if I run the program here, we can see that we will get up an image frame, and we will also get up the lidar frame. So first of all here, we can see that we get up the image frame, and we also get this map here where we have the robot and we have the marble, and then we have the green circles here is the estimates of the distance towards that marble. So we can see like the estimates here we getting from only using monocular camera geometry is fairly good, and we will only get like a small deviation. But the most important things here are the lidars, are the lidar points here, which is just like to show you guys what we can do with lidar and how it works in this simulated environment. And then we have this camera frame up here where we have this robot here that we can drive around with the arrow keys. And we can see that when we're driving with arrow keys here, we're detecting this marble here with the half circle transform, as we talked about in one of the previous videos. And then we can see that we're calculating a distance towards the marble from the robot, and also an angle from the center of the robot's field of view. So if I move a bit to the right here of the robot, where we can see that we get a greater negative angle, which is the deviation from the center of the field of view from the robot to the center of the detected marble. And if I rotate to the left here, that we can see that now we get a bigger positive angle, which is also the deviation from the middle of the center view from the robot. So if I'm driving closer to the marble here, that we can see that the distance towards the marble is decreasing, because we're driving closer to the marble, and the distance gets less and less the more like the closer we come to the marble. And again, we can see that when we're at like this distance here, like we can see that we get a fairly good tracking and detection of the marble. So the estimates and like the calculations of the distance and also the angle is fairly good, and we can see that the estimate of the distance here is like around 1.7. So we can use this camera geometry to estimate the distance and also the angle, and then we can have the robot driving itself towards that marble. So first of all, we have to orientate towards the marble, so the center of the field of view of the robot will be towards the center of the detected marble as well. And then we'll just drive a robot as long as the distance is greater than some threshold value. So we can also see, like, if we're driving a bit further away here, we can see that we still keeps track of the marble and we're still detecting it, we're still doing our calculations. But if we get too far away from the marble here, we start to get some flickering in detections, and we'll also get some false positives around in the image frame here. So we can see that now we get some false positive up here in the right corner. And if we drive too far back here, we can see that now we're just losing track and we're losing detections of the marble, and we can't really use the calculations of like the distance and the angle anymore. But it works fine if we're close or like relatively and having a medium distance towards the marble or a circle. Then our estimates and the angles, it works perfectly, and it just tracks the marble really good, and only like a few false positives once in a while. But if we get close to the marble here, like we get no false positives, our calculation is really good, and we can just like have our robot driving around autonomous, trying to collect these marbles here. So we also had the big world environment, and I'm probably going to do a video where I'm just going to show you the result and how we can drive around and collect the marbles or like the circles here in the big world environment where there's a lot of more marbles. So this is just like to give you an introduction of like how the program works. So let's now jump into it and see like how we can do the calculations, and also like how we can do the code for this project. So we're now back in the slides here, and I'm going to show you like how we can calculate these estimates of the distances and angles toward the marble. So first of all, we're going over to some slides here with some monocular camera geometry. So first of all, here we have our camera here on the figure here to the left. So this is a visualization of like the geometry that we're going to use in this project. So we have the camera down here, and then we can see that we have this field of view here of the camera. So this is the field of view that the camera can see, or like the robot can see with its camera. So we will have this angle here, which is the field of view, which is in this project here is 6 degrees. And then we'll have the focal length here. So we're using the pinhole model as we talked about in a couple of the videos that we've been over through this tutorial. So we're going to use the pinhole model here, where we have this image plane here, and then we will have the focal length, which is the length from the camera to the image plane that we're going to project, or like that we're going to detect our model in. And then we can do a 3D projection with our pinhole model from the 2D detected model to 3D with doing this projection that we talked about in the pinhole model. So in this example here, we're going to have the triangle here where we have the focal length here, which is the height here of this triangle. So this will be a right triangle. And we also have the image plane here, which is the width of the image plane. And then we can set up an equation for calculating the focal length, because we're going to use the focal length to try to estimate the distance towards the model that we've detected. So to calculate the focal length here of the camera, if we haven't, if the focal length is not given in the camera specifications, then we can calculate it with this formula here, where we take the width, which is the width of the image plane up here. So in this case, we have 320 pixels in our image plane, which is the width. And then we have this 2 times tangent here, because we're using the half of the width here, because we're only dealing with the right side of this triangle here. So we will have a right triangle of the right side here. So we take up the half of the width here, and then we're using the tangent to this angle down here. So this will be half of the field of view, so it will be 30. So that's why we divide the field of view by 2, because then we'll get this angle here. And when we know this angle here, and we know this distance up here, which is half of the image plane, then we can calculate the focal length here by using the tangent to this angle down here, and then divide it by the width up here, like divide the width up here by the tangent of the half of the field of view here. And then we will get the focal length here that we can then use to estimate the distance towards the detected marble. So we'll get this triangle here to the left that we can see that here, where we get this width divided by 2, because this is the right half of the original triangle. and then we will subtract the x value of the detected circle, like the center of the detected marble. We will subtract the x value from the half of the image plane here, because then we know the distance from the center of our field of view towards the marble, and then we can use that distance to calculate the new angle down here toward the marble. So in this case here now we know the focal length, and we also know the center of the detected marble by using the half circle transform. And we also know the half of the width of the image frame up here. So the only unknown variable or like parameter here is the angle towards the marble, which is this angle down here. And then we can calculate this by using this angle to marble here, alpha to the marble here, and then we're using the inverse tangent. So last time we used the tangent, but now we're using the inverse tangent to half the image plane up here minus the x value for the marble center of the marble, and then we divide that value here with the focal length that we calculated on the previous slide, and then we're taking the inverse or like the arc tangents to that value, and then we'll get this angle down here, which is the angle toward the marble, or like the deviation from the center of U, or like from this center line here to the marble, so that it will be that angle. So it will be deviation from the center of the field of view for the robot. And then we can also use this information here to calculate the distance to the marble, where we're going to use this focal length and also the width of the image frame, and like the half of the image frame. And then we're going to use the information that we get from the half circle transform, which will return the radius of the marble that we've detected. So with this information we have here, we can calculate the distance towards the marble with this this formula over here. So we take the half width of the image frame, and then we down here we have the radius of the marble, and then we multiply that with the focal length, and that will be the estimate of our distance to the detected marble in the camera frame. So this is the result from the marble detection that I showed you in the simulated environment as well. So we have the different kind of three different kind of angles towards the marble, and also 3 different distances. So the first one here is the far distance, so we're like now far away from the marble, and we take the distance to be 5.1 away from the marble. And also the angle here, we can see that it's a large positive angle, so we're deviating with 8 degrees from the center of the field of view for our robot. And we can see the same here for the other examples here, but this is just for another orientation and also another distance, or like a different distance towards the marble. And we can see the result up here to the left, in the top left corner, as I also showed you in the Gazebo simulator. So let's now jump into the code here, and I'll show you like how we can set up this code, and also how we can create this application to work with the simulated environment, and also like how we did the test and the demonstration that I did in the start of this video. So we're now in the Sublime Text here, and I'm going to show you the code for this project here that I've been showing you in the simulator, in Gazebo simulator, and how that works. So first of all here, we're going to include the Gazebo library here we're going to use to run the actual simulator. And then we're going to include the OpenCV library, where we're going to use the half circle transform function. So first of all, we have this camera callback function here, and what that does is it takes in every time Gazebo generates a new image frame from the camera on the robot in Gazebo, then it will send a message, or like a camera callback with a message to C++ here. And when a new image frame is received in C++ here, this camera callback function here will be called every time. So every time we get a new image frame, we will process it with this camera callback function here in C++. So first of all, here we just get the width and the height of the image frame from Gazebo with these functions here, so they're not really that important. And then we're going to have an image here where we're going to allocate, first of all, we're going to allocate some memory for the image that we're going to do the actual operations on. And then that image, we set that equal to the image frame that we get in from the Gazebo and in this message object up here. So first of all, we're going to convert the color from RGB to grayscale, because we want to do our operation on a grayscale image. And then first of all, we need to reduce some of the noise from the image, or like on the camera that from our Gazebo. So we're going to use this Gaussian blur here to smoothen out our image a bit more, and these are just default parameters. We talked about smoothing in one of the first videos in this tutorial, so if you're interested more in that and some of the parameters here that you can tune, go check that video out. Or also we're just going to use the default parameters here to reduce some of the noise, and this will help us get less false positives and also get a better detection result in the end. So first of all, and then second here we have the detection of the marbles, which has this half detection here. This is just like a helper function that calls the built-in function from OpenCV, but these are the two most important or significant parameters for that function. So this will be the canny edge detector threshold value, and this will be the accumulator value. So I also did a video on both canny edge detector and also the half circle transform. So check those videos out if you don't know like what these parameter does and how to use those functions here. So this is the project where we're doing some of the stuff and using some of the stuff that we have learned throughout this tutorial. So this is just like, we're just going to summarize the functions here, and if you miss something out or you want to know more about some of these functions, like you go check those videos out and you will get a better understanding of what's going on under the hood as well. So this is a helper function here that just calls this half circle detection. So if we go into the marble detection here is the actual like functions that we call. So down here is the half detection function here, which takes in the grayscale image, and then it outputs a new image. And then we get the canny edge detector threshold value and the accumulator value here as the two last parameters. First of all, over here we're going to allocate like a vector or like a variable here for the circles that we're going to detect from using this half circles. And we also have this double up here, which is the distance to the marble that we're going to return from this function. So first of all, we're going to call this half circle transform, which is the built-in function from OpenCV. So it takes in the grayscale image and then it outputs the detected circles in this vector up here, with the vector here of 3 floating points. So it will return the coordinates to the center of the detected circle, and it will also return the radius of the detected circle. Then we're going to use this method here, half gradient, which is the only method that we can use for, and that is built in the half circle transform function here. Then we use this one here, which is just like a scaling factor, and we have this gray rows here, which is the distance between the distances between the circles that this function is going to detect. And then we have this canny value and the accumulator value here, and this is the minimum and the maximum radius of the circles that we want to detect. But we want to have these parameters here variable, and they are as default if we just set them to 0, because we're moving back and forth with our robot, so we don't want to like specify what type of circle we want to detect. So down here we have a boolean where if we just is set to false, so we're going to check if a marble is detected, and a marble detected is as long as it is false, as long as like the circle's vector up here is empty. So we also have the closest circle detected here, which we're going to store in a variable, and then we're going to convert the color here again for like a grayscale image to the output image that we're actually going to display. So we convert it back here from the grayscale to RGB that we can show in our image frame. So to get the radius and like the outline of the circles that were detected, we're interested in the closest and the largest circles that were detected. So first of all, we're going to find the closest and the largest circles, because we want to just fill out all the false positives that were detected in our frame. So first of all, here we have a point here, which is the center of the circle that we've detected. So first of all, we have a for loop here that goes through all the circles that we've detected, and then we want to find the center of that circle here by taking the y coordinate and then the x coordinate for this circle here, or like the x coordinate and y coordinate, and then we have the center of the circle that we've detected, and then the radius here is the second or like the third element here in this circle vector that we have stored our detected circles in. So now we know the center of the detected marble and also the radius of the detected marble, and then we can use this function here, dis to marble, which we'll go over in a bit. So this distance to marble just takes in the radius, and we're just going to use the equation that I showed you in the slides to calculate the distance here to the marble. So to actually like draw the circle and like the output from our circle detection, we're going to use this circle function here. Actually like does it both. So this like does the same here. So the first one will draw like the center of the circle, and the second one will draw like the outline of the circle. So this is all it does. It just takes in the center and it will draw a circle around that. And the other one, it takes the center and the radius, so we get like the outline of the circle. So these are just functions to like actually like draw what we have detected with our half circle transform function. And then down here we have this. We check if the circle is the closest. So we say that if the radius is greater than one of the circle's radius, then we set the closest circle detected equal to I, and then we know what circle is the closest one. So down here we also have this angle to the detected marble, which takes in the circles that were detected, and also the closest circle that we're detected when we're going to calculate the angle to the model. But let's start here with calculating the distance to the model. So when we're using this here, we call this function calculate distance to model, and I have the function up here, calculate the distance to model, which just takes in the radius after detect the model. And first of all, here we have some conversions from pixels to millimeter, because we have when we're going to calculate this, we have our focal length in millimeters, and we want to calculate everything in millimeters, and then we can convert back and forth with just using this const parameter here, or a variable, or like this constant here, and then we have a double here for the distance and also for the distance to the model, and then we just set up these known parameters here for like the known parameters, or like the known constants here, as I showed you in the slides. So we have like the resolution of our image width, so it's 320, and then we convert it to millimeters. So we get all these constants here in millimeters, and we do the same here for our field of view. So we take the half of the field of view, and then we can calculate the field of view in radians, because when we're going to use the tangents in C++, it is in radians. So these are just like conversions between radians and degrees, and also pixels and millimeters. So to actually like calculate the focal length down here, we take the horizontal resolution in millimeters and divide it by 2, and then we multiply that here by the tangents of field of view in radians. So this will return the focal length of our camera here, and then we can use the focal length here to calculate the actual distance. So to calculate like the diameter of the detected circle here, we just take like the radius, like half the radius, and then we can have the detected diameter here of the circle, and multiply that with the pixels to millimeters, so we convert it to millimeter instead of pixels. And then we can go down here and have the actual like distance calculation, and these are just the exact formulas that I showed you in the slides. So we take the focal length times the horizontal resolution in millimeters, and then we divide that by the diameter of the detected model, and then the actual distance to that model is the distance times pixels to millimeter, because we want it in millimeters, and then we divide it by 100, so we get like the actual distance in our environment, instead of just having some unitless distance to a model. So we want to relate it from the model to the robot in the environment. So, and then we just return this distance here that we have calculated. So this is how to recalculate the distance to the model, and we can also do the same thing for the angle to the model, which is just the same formula as I showed you in the slides. So down here we just take in the circles that we've detected and the closest circle, and these are just the constants that we're setting up for calculating the angles again. So these are just all the known constants that we have, and then we can go down here and calculate the displacement ratio of the model. So this will be the x-coordinate of the circle divided by the width from the mid. So we take like the width from the mid, which we can see up here is the horizontal resolution times 2. So it's exactly just what I showed you in the slides, and then we can calculate like actual model angle horizontal change. So it will be the displacement ratio -1 times the horizontal field of view of the middle. So that's why we'll get like the deviation from the center of the field of view from the robot, and then we sometimes get a negative angle that we will turn in this case here when we're calculating the angle. So this is just so we can like try to converge when we are trying to orientate our robot towards the middle of the detected model. Then it will just go towards or like converge towards angle 0. And if there's the displacement in one of the directions, it will just try to like adjust for that displacement and try to go directly to the center of the model. So this is like how we can do the actual like calculations of the angle toward the model and also distances. And then we can just go into the main function here again, call these functions here, and do the operations on our camera callbacks, or like all the image frames that we get every time it gets updated in Gazebo. And then we can just show the image here we can just show the image here that we're doing the actual like operations on, and also output the distance and the angles as I showed you in the simulated environment. Down here we just have the main function where we like initialize all the things we need for like the Gazebo, for having this camera callback function and doing some setup. So this is not really like the most relevant stuff for this project and doing something in computer vision and doing what we have learned in this tutorial. So this is just like how we can operate with a simulator in C++. And also down here we have some other different kind of stuff where we just load in like the floor plan and we do some logic here with the key arrows. So I moved around with the robot with the key arrows. So I change the speed and the orientation, or like the direction for the robot, by just using like the right key, like right key and the down up key and stuff like that. And then we just send that value to like this pose here, and it will generate a pose and send that out to the pose, or like the movement populaces of Gazebo. So this doesn't really matter at all. It's just like how we can get something from C++ and into our simulated environment, and like test what we have created in C++ here, and test our project, see how it works, and then we can go back into our C++ project and then tune some parameters and like debug what's wrong. So that's pretty much it for this project here that we've been doing, and this is just like to summarize some of the things and use and most of the things that we've learned throughout this tutorial. So it's a really good practical example of using a lot of different kind of things at the same time, and also having a simulated environment where you can actually like see what you've created. So I think this project is really good for beginners, and also like doing it for gaining as much knowledge as possible, but also doing some of the things that we learned in this tutorial in a practical way, and also like actually doing a project is really important for learning. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more in the future. It really helps me and the YouTube channel out in a massive way, and I really appreciate your support. So I'm currently also doing an artificial intelligence tutorial where we're talking about reinforcement learning, and also an algorithm data source tutorial in C++. So if you're interested in one of those tutorials, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.